Um, desktop one, that should be good. Can everyone see my screen?
Yes.
Okay, perfect. Okay, so thank you very much for having me here. Again, hi Ryan. I run into Mark every once in a while, and it's great to see Mark again. Professor Lee, I saw you in the on video, so you know, hi again. It's been far too long, I must say. Okay, so let me get on with the talk. Thank you very much for having me. It's delightful to be back there. You know, online, if not in person. I'm sure that you know that I'll come to LSU, I'll come to Tulane and visit all of you all once once this thing settles down. So okay, so let me just talk to you about some work that I've been doing with students and colleagues over the last 3-4 years. So this is quantum synchronization. It's the area of quantum synchronization, and it's just in the spirit of what I learned at LSU. It's the spirit of what I learned from John, and in that it is in part you know, a fundamental research which has strong applications. So with that little thing, let me begin by basically saying. Okay, let me begin by first motivating the problem to you, because you know quantum synchronization sounds a little bit distant to all of us who are used to quantum information theory and its peripheries. So here is what quantum synchronization is useful for. Let me begin by saying that to you. It's useful to set up things such as single atom masers. So there's strong quantum optics applications here. So this is a paper by Vahala in 2009, where the Van der Pol oscillator, which I'll get to in a second, was used basically in setting up a single atom maser. We used it late last year basically to point out that the coherent output of a thermal maser is actually can be thought of as a synchronous object, and so synchronization has strong applications in quantum thermal machinery. You know, synchronization is a mechanical phenomenon, as I'll show you in a second, and so given the fact that we can we have nanomechanical oscillators and optomechanical oscillators, which are basically near the ground states of their motion, this provides us with a tremendous opportunity basically to try and do some nonlinear dynamics inside of those quantum systems, and the applications thereof are basically really tremendous. For example, one of the things that I won't talk to you about today, but this is ongoing work, we're just writing it up, is to construct basically multipartite entanglement engines. So this is work from Jonathan Bohr-Brask's group. But what we've done is we've taken the approach of synchronization, and we've built a synchronous machine which basically behaves like a multipartite entanglement engine. Lastly, I just want to say that there is a tremendous excitement about atoms inside optical cavities. Things like Bose condensation, photon condensation. These things are basically in the literature now, and a lot of quantum control and manipulation is possible now, which is very exciting. So these kinds of coupled optomechanical systems alongside atoms. This is the kind of scope of the work that I want to talk to you about today. So with that, let me introduce the outline of the talk. So what I'm going to do is I'm going to introduce synchronization to you. I'm going to talk about classical synchronization, and then move on to the quantum version of it by analogy. And I'll make many hand-waving arguments, but please pin me down on anything that you want to know the details of. And I'll introduce you to one of the problems that we essentially try and resolve, which is the zoo of measures that exist in studying synchronization. And so this top part of the talk is basically going to be a combination of nonlinear dynamics and quantum optics. And so hopefully that's of interest to some subset of people here. I know Ryan is perhaps quite interested in that. But then I'll move on to the stuff that everyone else is definitely hopefully interested in, which is basically the information theoretic part of the talk, where I'll basically point out that our understanding of information theory actually has some has capacities to solve some of these problems that have come up in the recent past in trying to experimentally characterize what's happening, and and in trying to reduce the number of existing measures basically that that have popped up. I'll finally conclude by basically pointing out that our measure, the generalized measure of quantum synchronization that I'll introduce, actually reduces to some known measures in the field, not just of synchronization, but also in known measures and quantum information theory in general. And so that's quite exciting to us as well. Okay, so with that, let me talk about quantum synchronization. I'll follow the show not tell mantra and just show you what quantum synchronization is. So what it is let me just pause this video for a moment. It's two metronomes that are basically on a platform, and the platform is on basically two cola cans, basically. And so what you see is you're going to see them start off basically asynchronous with each other, which is to say that their rhythms are not adjusted, are not locked, and then they will basically lock to each other's rhythms. And the locking basically happens because this little platform that they're sitting on is communicating the energy back and forth and makes it possible, basically. So let's just view this. And you can see visually perhaps that that there is now kind of an alignment of the rhythms. So this is basically what synchronization is. This was something that was discovered by Huygens many years ago. And what this gentleman is doing right here is what this gentleman is doing right here is he's basically disrupting the synchronization in the middle. And when you disrupt it and you let it go, it's very robust against perturbation. So it just relocks itself. So that's quite nice phenomenon. Okay, so how do I think about this mathematically? So the way to think about this mathematically is basically it started off with ordinary differential equations. So here is kind of the canonical example. This is the ideal gas of classical synchronization. So the first simplest model devoid of all of the kind of unnecessary details. So these are basically what are called phase oscillators. So a phase oscillator is an oscillator basically which can move along the phase degree of freedom, but whose radial degree of freedom is somehow locked away. I'll show you examples of this in where the X and the Y axis will actually be position and momentum. So it will be actual phase space in which we're having this conversation. But for now, just imagine that there are basically just beads on a ring and on a rigid ring. And these beads are basically talking to each other. For instance, if they're charged beads, then they basically will repel each other, and that's a kind of interaction that exists. And so what Kuromoto did in 1984 was basically was modeling chemical reactions, and he basically pointed out that you can have, if you write down a differential equation as simple as this, theta I dot is sine theta j minus theta I, then basically for some coupling Kij, this has the behavior basically that all of the phases that are sitting around, they will lock to each other. I'll actually show you a movie of this in a second, but that's classical synchronization in a mathematical formalism. So going from the physics, from the experimental demonstration, this is how you would basically begin to do the analysis of synchronization. Right. So let me just point out that in this example, what I had shown you was bidirectional coupling, which means every oscillator is coupled to every other oscillator. So so it's a little bit like decay superradiance. There are many examples in physics which follow this kind of behavior. You could do something else as well. You could imagine basically an even simpler problem. So the simplest kind of ideal gas problem that you can imagine is you just have two oscillators, and one of them is very heavy, right? So if theta 2 is very heavy, then but it's moving with some frequency omega 2, then theta 2 basically absolutely does not care about theta 1 because it's much heavier than theta 1. But theta 1, on the other hand, is still influenced by theta 2. So this is basically a unidirectional coupling. This is quite common in electronics, basically. Is still quite common in electronics. It was known by the kind of somewhat unfortunate phrasing of master-slave circuits. But that bad phrasing aside, the meaning of it is basically that there is one person who's leading the frequency locking and the other one that just locks onto it. The meaning, that meaning when it translates over to physics, for me is basically an example such as this, where I have, let's say, a nanomechanical resonator with some qubits embedded at the end of it. So I'm already kind of motivating the quantum version of it as well. And I basically just wiggle the nanomechanical resonator from the outside. So that's a classical external driving that basically there's no way for the quantum system to do feedback onto it, and that's theta 2. Whereas the qubits, for instance, are responding, if they're sitting in an anisotropic magnetic field, then they'll respond actually to the magnetic field. And that's basically this first part here. So that's the way I want you to think of this. So I'm sorry, this is a bit of a busy slide, but let me just say there are only two things I want you to take away from this. One is I want to justify basically why I need a nonlinearity, why this is in the realm of nonlinear physics and not linear physics. And the answer is basically provided here. So what I've plotted is some general coordinate. That's the reason I didn't even bother labeling it. I have plotted two processes. One, let's say, is a linear pump. So it just, what happens is that as you go further along this axis, the energy is simply increased. Whereas this little curve is a nonlinear damp. So it's a damping force, but it's nonlinear. And the reason it has to be nonlinear is so that it can cut this line at some finite point, and you can understand that two straight lines won't ever cut each other because they have to meet at the origin. And hence having a nonlinearity is intrinsic towards finding an energy balance point, where the amount of energy that is given by the linear pump is taken away by the nonlinear damp. And you get an energy balance situation where there is this stable limit cycle. So the stable limit cycle, or that fixed ring that I was just talking about a second ago, is actually just an example where there is energy balance and the two dissipators, one of which is a pump and the other which is a damp, cancel each other in terms of energy, and the system just sits there, right? Now, how does this object behave when you drive it from the outside? How is that driving any different from just a resonance effect of a damped harmonic oscillator? It's different in this in the way that is depicted in this particular diagram. So here is basically on the x-axis, I'm actually plotting the driving frequency. So I'm plotting this frequency with which I'm driving the external oscillator. And on the y-axis, I'm actually plotting what I observe as the observed frequency. And I've just taken away the driving frequency just so that I can kind of have some simple units. And what you notice is basically that the hallmark of synchronization is what is called this region of synchronization. This is actually entrainment because it's an external oscillator driving a single system, but this is an unnecessary detail. So the hallmark of synchronization is the fact that when I detune a little bit, so when I am driving, let's say, a 1 megahertz resonator at 1.1, 1.2, 1.3, the resonator stops oscillating at 1 megahertz and oscillates at 1.1, 1.2, 1.3. There is complete phase frequency locking to the external drive, right? And that's very, very different qualitatively from just a damped harmonic oscillator. Of course, you can imagine that if you drive a 1 megahertz oscillator at 3 megahertz, it's not going to respond. So after a while, it uncouples from this basically from the external drive and goes back to its natural frequency. And that's that little curve there. So what I've plotted here is basically, I've just borrowed this from Pikovsky's book. What I've plotted here is a simple intuition that we would have, which is the one thing that has not entered into the discussion yet is the driving frequency. What role does the driving amplitude, sorry, what role does the amplitude with which I drive, what role does it have in terms of the region of synchronization? What I would expect is basically the harder I drive an oscillator, the more it will respond to me. And so that translates here into the fact that the harder you drive, so along that axis, you're increasing the forcing amplitude, the larger the region of synchronization is. So for a larger frequency detuning, the oscillator follows the external driving. So that's the point here. Okay, so with that little introduction, let me bring you to the first mathematical example. And I need this because I'm going to show you the quantum version of it. And this is what's called the Van der Pol oscillator. So the Van der Pol oscillator is basically, the first three terms here are just the damped harmonic oscillator. The last term is just forcing. The only kind of strange thing about this are two things. There are two strange things about it. One is that there is a gamma 2 x square x dot. So there's a nonlinear dissipator. And the other is that the signs are wrong on these two, basically. So this is a linear pump. If I flip the sign, it would just be linear damp. And then that would just be the damped harmonic oscillator. Whereas this term is a nonlinear damp, right? And so it's exactly the same that I just told you a second ago. There are two technical steps here, which I will just briefly mention. One is basically, I want to convert a second order ODE into a first order ODE because I want to match it against quantum mechanics. So, well, you can do it otherwise, but just for convenience, what you can do is you can complexify X. So if you write X as beta e to the I omega plus beta star e to the minus I omega, where omega drive is this drive frequency with which you're driving. So you get into the drive rotating frame and then you complexify. Then that's step one. And step two is basically you do something called Bogoliubov-Krylov averaging, and you end up with this equation, which I will show you again. You don't have to remember anything about it. The only thing I want you to take away is gamma 1 is a linear dissipator, so it just comes as gamma 1 times beta. Gamma 2 is a nonlinear dissipator, so it comes as gamma 2 mod beta square beta. So there is that cubic term there that indicates to you that that's the nonlinear term. So how does this oscillator behave, basically? That's what I've plotted here. So just focus on the mu equals 0.1. Mu is gamma 1 equals gamma 2 equals mu. So mu equals 0.1 basically already tells you the difference between this and a harmonic oscillator. So a harmonic oscillator, if you just look in phase space, an undamped harmonic oscillator, what it does is it has an ellipse, right, defined by basically the constant energy that you supply it. Now, if I give it slightly larger energy, the harmonic oscillator will just go settle in a slightly larger ellipse, right, such that the energy is its constant energy surface. So the harmonic oscillator is actually agnostic as to what ellipse it wants to settle in. It settles in whatever energy that you give it. That's the ellipse it settles in. Whereas this oscillator is completely different. So you can see I've started it inside this kind of circle here. And what it does is it just drives itself to that circle, right? So this is what's called limit cycle behavior. And once you have that, what it does is it's just oscillating on and on and on. And that's the phase oscillator, right? So the phase of X versus P is that phase oscillator that I'm trying to log. So that's what I want you to take away from this. Now, before I move on, I just want to highlight, why do we care about any of this? Well, the reason that we care about any of this is because it's ubiquitous in nature. So here is an example of actually fireflies which are blinking in unison. So this is an example where in Thailand, I think, the experimenters, what they did was they took LEDs. So these are the LED lamps that you can see here. And they got fireflies which basically blink to actually blink with the external oscillator, which is the LED. So you can see them actually blinking right now. Not everything that you see is just the LED, right? And so this is one example. Another example is the circadian rhythm. It's just the fact that every day when we wake up, we have the desire to eat at around breakfast. You feel sleepy at the right time. All of this is basically driven by the fact that natural light enters our eyes, and it triggers basically things like serotonin release and so on and so forth. In fact, a late night consumption of electronics is associated with lack of sleep for exactly this reason. You're disrupting that oscillator. Here is the Van der Pol oscillator. It's actually the physical analog of it is a triode. And so that example, the mathematical example that I showed you already, is actually a well-known classical physics example. And the very last example that I just want to show you is what's called the Belousov-Zhabtinsky reaction. It's a chemical reaction which basically just keeps oscillating. So you just see images like this or videos like this. And this is described by basically a spatially varying Kuromoto oscillators coupled to each other. So this is the kind of physics that, so the central point or the takeaway from this slide is basically that synchronization is everywhere, and you should pay attention to it because it's everywhere, right? And so that's the reason why we also think that synchronization will be very, very interesting in the quantum regime. So just a couple of takeaways. So nonlinearity is needed to induce self-oscillations as limit cycles. Perturbative driving is necessary. I'll justify that if anyone's interested. And you can either drive a single party from the outside, that's what's called entrainment, or you can couple several of them and you can ask them to basically phase lock. And this is an example of that. You can see this is the Kuromoto, a simulation of Kuromoto, and you can see that they phase lock as they go along, right? Okay, so that's the little introduction. With that, let me get into quantum synchronization. So because I've already motivated to you that I need something linear, something nonlinear, I can just walk you through this Lindblad equation. So this Lindblad equation has an external drive H, which in the rotating frame basically has a detuning. This detuning captures the difference between the drive frequency and the natural frequency. And the F is the force amplitude. And I have a linear dissipator gamma 1, which is simply a linear pump gamma 1. It pumps you linearly, and a nonlinear damp. It's a 2-photon damp, basically. And what Walter Bruder-Noonan pointed out in 2014 was basically they said, if you compute the expectation value, the equation of motion for the expectation value of the annihilation operator, it follows the Stewart-Landau oscillator, right? So here in mean field, you have something which is a one-to-one match to a nonlinear dynamics model, right? And that's the kind of beginning of this conversation, one of the beginnings of the conversation. So here is what you would see if you wanted to check the quantum versus the classical. So the classical motion is actually given here by this circle. So this is classical motion of the classical Stewart-Landau oscillator for some value of delta, gamma 1, gamma 2, and omega. Right? Omega is the same as f. I'm sorry, this is a typo. Omega is the same as f. And for these values, basically, all you see is that circle. Now, if you solve the quantum mechanical problem, which means you solve this Lindblad equation and you plot the Wigner function corresponding to it, you see it sits very nicely overlaid on top. So here is another place where basically the measure of synchronization is something that that first pops up and becomes a huge problem that I'm going to point out, which is so the way these folks basically even describe how to measure synchronization. They do several things. First, they say, well, we can use something like the Peg and Barnett phase operator, and we can check what the phase distribution is. Here, clearly, you can just eyeball it. It's uniform distribution in the phase direction. Whereas here, for some other variation of parameters, you can see that they are localized around some value of phase. There is a phase preference here. If you drew the mean arrow, it would point somewhere here, whereas the mean arrow here would just have length 0 because it would just be sitting in the center. So they said you could do that, or you could basically also do something more complicated, like look at the power spectrum, blah, blah, blah. So following on, what Bruder, along with Alex Roulet, what they did later on in 2018 is they said, well, we can actually generalize this even to 3-level atoms, and we can do it for spin J systems in general, basically. So how do you go about it? There's nothing special about the Wigner function. You could just as easily have chosen the Husimi-Kano Q representation function. And for kind of mathematical convenience, this is simpler to define. So the Husimi-Kano Q representation function is defined as the expectation value of the coherent state of the steady state density matrix. So let me just back up a minute. I forgot to mention this. I take this differential equation, I plot its steady state, I compute its steady state, and that steady state is what I'm plotting here. So, so you should keep that in mind. Now, what Roulet and Bruder said was, they said, well, you could take this Husimi-Kano Q representation function and you could basically ask, so it's defined this way. It's defined for SU2 coherent states. It's defined for equally spaced 3-level atoms. It's essentially defined as in terms of 2 angles, theta and phi. So what they said was, they said, well, you could go through the motion of trying to figure out what the free phase is. What does the free phase even mean? So if you plot the free dynamics, you'll see that one angle basically doesn't vary at all, whereas the other angle varies quite a lot. So what they basically said was, they said, oh, this is the free angle. This angle that's horizontal is the free angle, whereas this is the not free angle. And the not free angle physically corresponds to the population, basically. So let me just quickly say that. And so they said, okay, so you can construct a formal mathematical measure of synchronization. And the way you do it is you take this Husimi-Kano Q representation function and you integrate out the population dynamics because you're uninterested in it. And then you basically check against the uniform distribution to see if there is any synchronization. So this is a very tedious measure of synchronization. And what you will see for states which do exhibit synchronization or entrainment is basically that there is localization not just in one direction, but in both directions. So this guy is localized over here. And if you plot basically the Arnold tongue, the corresponding Arnold tongue basically appears basically, you can see the Arnold tongue. So let me just walk you through this. So this is detuning on this axis, which means that I'm basically increasing the drive frequency with respect to the natural frequency. And on this axis is the strength. And you can see that as I increase the strength, the region of synchronization grows larger and larger. That's the same story of classical mechanics now sitting inside a 3-level quantum optics problem. Okay. So we studied thermal machines, and for thermal machines, we needed to generalize it not just to the SU2 subgroup of SU3, but the full SU3, which is to simply say a general 3-level atom. And immediately what we realized was that this is not going to work very well because it's very tedious. The whole conversation is very tedious because, for instance, for the full SU3, you need to have 4 angles. This is not very difficult to figure out why. So let me just describe what Xi is. Xi is the ratio of the second to the third population. Mod square of this by mod square of this is cotangent Xi. And theta is the population ratio between the first and the second plus third population, right? It's the ratio of the population. And phi1 and phi2 are the relative phases of the second and third with respect to the first. The 1 gauge degree of freedom is irrelevant. So that's just the way to think about basically what this atomic coherent state is. And you can construct a corresponding Q function. It will have 4 angles, right? The previous one had 2, you integrated 1 out. Now we have 4. And you can work out that you should integrate 2 out because you integrate out the population dynamics. So you can see very easily, right? I mean, the construction is tedious. It takes and it takes many angles. It consumes many angles. So this 3-level engine problem that we worked out is actually it's on a toroid. It basically has 2 phases attached to it. So then basically what we realized is that this is not going to scale very well. So we could solve a driven qubit. This is actually the thermal atom that I showed you. You could couple 2 qubits for some specific approximations, but you couldn't go beyond that. If you try to do cavities coupled to kind of atoms or optomechanical cavities with several atoms inside it, this whole thing would just become very messy. And where is the mess coming from? So let me point out where the mess is coming from, and I'll take the next 10 minutes just showing you the solution. The mess essentially is coming from the fact that the limit cycle, the nature of the limit cycle keeps changing. If I have a Van der Pol oscillator, it's a harmonic mode, which is basically phase delocalized. On the other hand, if I have a 3-level atom, it's either a thermal state or it's some diagonal distribution, right? So the details of what the limit cycles look like keep changing, and that's the thing that's creating all of this part of this confusion. And here is where I just want to bring in the quantum information a bit and walk you through the rest of the conversation, which is we've been here before, right? We've been here before because this is exactly how we discuss entanglement measures, right? Suppose I want to discuss fully separable, the distance to fully separable states versus biseparable states. All that can be handled now, basically, even though there are tons of angles attached to basically the description of the quantum states. None of this is threatening to us anymore because we actually know how to deal with it. So you either define, let's say, a relative entropy, any distance, well-behaved distance measure, or trace distance, which are the 2 distances that we consider. And you define your set of states carefully, and you just do a minimization. You just go through that procedure, right? So what we did was we followed the exact same procedure, and we said, well, let's construct a new measure of quantum synchronization, a unified measure. And the unified measure is basically the minimization of an appropriately chosen distance, relative entropy or trace distance. We worked out both cases of your given density matrix to the set of limit cycle states. And the rest of this this talk, I'll simply describe to you what the limit cycle states look like. So one interesting case of limit cycle states is, for instance, things like this. So here is a thermal atom. So thermal engine, what it means is it's a 3-level atom that I'm coupling to 2 heat baths. And what it does is it goes and settles in some non-equilibrium state, but that state is actually diagonal. It just only has diagonal entries in it. And so, and so this kind of an example is one where I'm interested in a diagonal distribution, right? So my limit cycle is actually a diagonal distribution. On the other hand, I could basically demand that I'm not interested in what is happening to the local states. The marginal states are irrelevant to me. Please tell me if there is some relative angle, in some sense, some relative angle between the 2 states which are locking onto each other and which are getting localized. And this notion would basically be, bring us to the limit cycle set being a marginal set of limit cycle states. And the third is basically a partially coherent limit cycle. This is one of the breakthroughs of our work. Here, basically what we're doing is we're allowing ourselves to kind of have complicated examples, which are, I think, real life examples. So for instance, you could consider a 3-level atom like this, which is already being driven across the 2-3 transition. And you could have a Van der Pol oscillator, which is already phase localized because it's also being driven. And now you could say, I want to switch on a coupling between these 2. I can't control the drive for some reason, the local drives for some reason, and I want you to take it out of the physics. So I want you to tell me whether they phase lock with each other over and above the fact that they're being locally driven, right? And that really brings you to the full context of all of the applications that are available to us. So let me justify, right? So in doing all of this, I presumably have justified to some extent at least the fact that I have, let's say, a diagonal limit cycle or a fully marginal limit cycle, so on and so forth. But why a set? Where did the set come from, right? I mean, we understand where the set comes from in entanglement theory. Where does it come from in this physics? Where it comes from is basically something very simple. So here is an example again. Suppose I have a Van der Pol oscillator, and basically I don't touch it. It's not driven, and its limit cycle is something like this. So I solve the quantum, I solve the classical, and here is a limit cycle. What I then do is I switch on the drive, but the act of switching on the drive, basically, because you have to rederive the master equation technically, and Kurt, I'm looking forward to Kurt's talk on this. When you rederive the master equation, suppose you added one more term to Lindbladian because, because whatever, right? So I'm just saying indirectly in words, what I'm saying is I just heated the system up by just switching on the drive. Then what happens is that my limit cycle could be different, but I've switched on a laser, which means now it's phase locked around the new limit cycle. So what that means is that if I didn't allow for all possible sizes of circles, I would actually not only account for the fact that my donut went into this little blob, but I would also mistakenly account for the fact that the size of my donut went up. I'm not interested in that. That's phase agnostic, and that's not something I care about. And that's the reason why I want to take it out. And what the set allows you to do is it allows you to minimize over all the limit cycles and take it out. So so here is the summary again. So if you have if you don't care about the local coherence at all, then you have basically the full marginal limit cycle set. If you care about, if your local states are guaranteed to be not coherent at all, then you have diagonal limit cycle sets. And if you have something in the middle, then you have these partial limit cycle sets. And here is an example. Let's say the 1-2 transition in this example is being driven. So you have some 1-2 physics here, but you want to know if something more is happening. Okay, so let me knock out the simplest problem. Yeah,
you should probably wrap up to allow for questions. You have 2 minutes left.
I'm almost done. I'm completely done. Yeah, so let me wrap up by just taking you through 1 or 2 examples. One is mutual information. So if you choose the limit cycle set basically to be marginal states, then you can easily see that this is just, if you choose the relative entropy measure, then it's just the mutual information. And this actually brings us down to one of the examples that's been worked out before by Sarufazio, Giovanetti, and Ameri. So this, let me just point out, this doesn't work for unipartite systems. So this is only bipartite measure because mutual information is only for bipartite measures. What we also were able to show was that if you do it for unipartite measures, so if you do it, if you apply our generalized measure for unipartite measures, then basically what you recover is this resource theoretic quantity, which is the relative entropy of coherence. So the relative entropy of coherence actually pops right out of our calculus and for a particular choice of the limit cycle states. And here is the corresponding Arnold tongue attached to it. And likewise, here is a kind of complicated example of a 3-level atom coupled to a van der Pol oscillator. It's the exact example that I just showed you a second ago. And we can work it out. And here is the Arnold tongue corresponding to it. And the very last thing that I just want to point out is that we also worked out the exact formulas for partially coherent limit cycle states for 3-level atoms, basically. And the partially coherent limit cycle states, it just involves a small trick with respect to how to compute the unitaries, and you can work through the formula. So the bottom line, and I'll conclude with this slide, the bottom line is basically that we can do all of this now. So we can consider all of these variety of examples that I began the talk with. So so that's my concluding slide. So let me just thank my co-authors on this. Noufal is an excellent postdoc who's with us. Mikal is in Singapore, was in Singapore and is now in KO in Japan. Parvinder is my graduate student. Kwek is in Singapore. He is my boss in Singapore, and Sarufazio, who's at ICTP right now. And let me just say what a great pleasure it is to be here. I miss John dearly. And several of the people who are in this picture are in the call right now. So I just want to register that it's a bittersweet moment for me, and I'm happy to take questions.
Excellent. Thank you very much, Sai. That was a wonderful talk. Does anyone have any questions for Sai? Just go ahead and speak up if you do.
I think we're a little over time, so we should probably, if you have questions, send an email to Sai. I think it's important to stay on track because people are going to be tuning in and out during the day. And, like I think Kurt has a specific window for his talk, so we want to make sure we're on track. So thanks for the talk, Sai. Appreciate it.